Hello, everyone, and thank you so much for joining us today. Welcome to this joint ISC Epstein seminar, CAIS seminar, and CS Distinguished lecture. I think it's the first seminar that has so many joint, audiences together, and it's definitely worth it. Because today our speaker is Professor Milind Tambe, and it's my huge honor to be able to introduce him and host him today. So Professor Tambe is a Gordon Mackey Professor of Computer Science at Harvard University. He's also a principal scientist at Google DeepMind. His research is focused on AI for social impact and really on deploying the AI tools that he's created to make provide benefits for society, in particular in the areas of public health and conservation. He has received more prestigious awards than I'll have time to list today, so I'll just mention a few. He's received the AAAI award in AI for the benefit of humanity. He's received an HKAI John McCarthy Award and an Informs Wagner Prize for Excellence in Operations Research. So you'll see that a lot of his research is actually at the interface of AI and OR, so very relevant for the audiences today. I have the immense fortune to have worked with Milind quite a bit over the past few years. And really the main thing that stands out is beyond his kindness and humility is really how passionate he is about his work. And just through his talk and by talking to him and listening to him, I'm sure that he'll be able to motivate you to try and do work just like he does. So Milind, it's a great honor to have you here today.
Thank you.
Very excited about your talk.
Thank you so much. Thank you. Well, thank you for that kind introduction. Thank you all for being here. It's a huge honor to have Gaurav and Nino and the CAIS people here. So really amazing, and thank you all for being here. So for the past 20 years, my team and I have been focused on how to advance AI for social impact, focusing on topics of public health, conservation, and public safety and security, with the key challenge of how to optimize our limited intervention resources. The main lesson learned is that social impact and AI innovation often go hand in hand. I wanted to give a quick tour of some of the work that we've done, particularly for some of the new people here. And this is also expressing my gratitude to USC. So with respect to public health, we have large populations to serve limited number of public health resources. So concrete example is work we have done with youth experiencing homelessness in Los Angeles. Harnessing the social networks of these youth, we are able to show that our influence maximization algorithms are far more effective in spreading HIV information and reducing HIV risk behaviors compared to traditional approaches. I'll have a little bit more to say about this a little bit later on, but I'm extremely grateful for the joint work that we were able to do with Professor Eric Rice, and he opened the door to all of the work that followed for our group in social work and public health. With respect to conservation, we have large conservation areas to protect limited number of ranger resources. So concrete example is work we have done in Uganda and Cambodia. We're harnessing past poaching data. We are able to predict where poachers set traps or snares, and for the past several years have been able to remove thousands of these snares. This work requires innovation in what we call green security games, which combines machine learning and game theory. And here I'm grateful for the work that we have done with Professor Bisra Dilkina in Cambodia, for example, in trying to find these snares and removing them. With respect to public safety and security, we contributed a new model called Stackelberg Security Games. So this was right after 9/11, and contributed new algorithms based on this model that have been in use by security agencies in the United States for a decade or so afterwards. For example, with the Federal Air Marshals, with the US Coast Guard, to do patrols in the ports of Boston and Los Angeles and New York, and at the LA airport. And so we've been on a US air carrier since 2009, Delta, American, or United, whether, international flight, whether there was an air marshal or not on your flight, was our code. And again, I'm grateful for the work we were able to do with Professor Phoebe Vianos in this area of public safety and security. But today, I'm very excited to share with you our work that we've been doing recently in Bandit algorithms and agents. The talk is divided into 4 parts. The first 2 parts are field results from world's 2 largest maternal mobile health programs. First is with restless bandits. And here I'll focus on the M-Mitra mobile health program where 200,000 mothers are registered at a time. The second is with collaborative bandits. This is Kilkari. This is India's national maternal mobile health program where at least 3.5 million mothers are registered at a time. So these are actual field results. I'll next focus on HIV prevention. This is work we're doing in South Africa. And here we'll use branching bandits for improving HIV testing. And we're very excited for the future field trials. Final part will be multi-agents for speeding up social impact. Here I'll talk about LLM agents being useful. I'll highlight the role of the lead PhD student who did the work by putting up their picture in the top right-hand corner of the slide on which their work is shown. So let's begin with maternal health. So the motivation here is the maternal health crisis we face today. The UN Sustainable Development Goal says that by 2030, maternal mortality ratio, mothers dying during childbirth or soon after, should be below 70 per 100,000 live births. Where we are today, the dashed line is the UN target. In Western Europe and United States, the numbers are lower. But worldwide, the numbers are more than double the UN target. Now, this seems like a global problem, a problem that's out there, but it's also a problem right here. In states like Mississippi, for black mothers, for example, the maternal mortality ratio is 20 times worse than what it is in countries like Greece and Slovenia. So it is a global problem. We are going to focus here on the challenges in India where the numbers are rapidly declining, but still higher than the UN target. We've been very fortunate to be working with a nonprofit called Arman, which works with more than 40 million mothers in India. So in consultation with Arman, the first problem we focused on was the M-Mitra mobile health program for new and expecting mothers. So a mother registers, and every week she'll get a 2-minute audio health message. And so a small snippet of this message is something like this: for you and your baby to be strong, you need lots of iron. Iron-rich foods include meat, jaggery, and leafy green vegetables. This is a small snippet of a 2-minute audio message delivered in the local language of Marathi or Hindi or what have you, and in a sing-song fashion. And there's 141 messages from the time the mother registers to the baby being 1 year old. Over 3.6 million mothers have benefited from this program. And in randomized control trials, Arman has shown that as long as mothers listen to these messages, there's significant benefits to the infants and the mothers. For example, 30% increase in infants with triple birth weight at the end of the year. So it's all working great. Where do we come in? Unfortunately, 40% of the mothers who register drop out of the program or become low listeners. What can we do about it? There's a call center Arman has from where they can give a limited number of service calls to try to persuade mothers to not drop out. And here's the challenge. We have 200,000 beneficiaries, mothers registered in the program. Remember, every mother, every week, always gets an audio health message. But from the call center, we can only call 1,000 of these mothers to try to persuade them to not drop out of the program. So which 1,000 out of the 200,000 to call in order to maximize the total number of health messages that are listened to? And one big challenge here is the dynamic state. So mothers may change state on their own. They may be in a bad state, they have not listened to a health message, and they may go to a good state, or vice versa. And even if we give them a service call, they may or may not change their state. So to illustrate this, consider that this call center in this illustration has only 5 mothers under their care. 3 shown in red have not listened to a health message last week, and 2 shown in green have. And we have a budget in this case just of 2 calls. Supposing we call the first 2, we expect next week maybe there'll be 4 in green who start listening. But in fact, in this case, this doesn't work out. One of them we call turns to green, and another one who was in green also turns to red. We end up with 2. Again, it's budget of 2. Who do we call? We expect there's 2 green. We call 2 more. We expect them to be 4 green, but we may end up with nobody listening now because we picked the wrong people. So to deal with this problem, we use the notion of restless bandits. So this is an idea to choose k of n beneficiaries with dynamic state. For those of you who may not be familiar with restless bandits, in each arm of the bandit is a Markov decision problem. So each mother is being modeled as an MDP. So mother might be in a bad state. She has not listened to a health message, or a good state. She has listened. We can intervene by calling her, giving a service call, or not. And now there's transition probabilities that model the behaviors of the mothers. For example, if the mother is in a bad state, we give a service call, the probability of going to a good state is 0.8, but if you don't, the probability drops to 0.2. In reality, there's 200,000 arms, so there's 200,000 mothers, and here we have to choose 1,000. So essentially, we want to choose a policy to choose k of n mothers every week, such that we maximize the total number of mothers in the good state, where good state gives us a reward. This problem is known to be p-space hard, and so the idea then is to use what's called a Whittle index as a heuristic approach. There's an algorithm we developed back in almost 2016, and so formally the Whittle index says, what's the infimum subsidy I can offer to the passive action in a state such that its Q value becomes equal to the Q value of the active action. Informally, what we are doing is computing what's the benefit of intervening on this mother. And so we can therefore rank 200,000 mothers using this Whittle index and pick the top 1,000, which gives us the greatest benefit in terms of intervention. But this Whittle index requires us to know the transition probabilities, which we don't have. So we learn those from past data. So for each mother, we have features like age, income, education, etc., and data. The mother was in a bad state, got a service call, bad state, service call, good state, etc. So we can now learn a mapping from the features of the mother, like age 26, income 5,000, education is 8th grade, probability of going from bad state to good state is 0.3. So when a new mother walks in, we can predict the transition probabilities for her MDP. And next, we can optimize by choosing the top k mothers using our Whittle index. We call this the two-stage approach because we first maximize learning accuracy, and then separately, we optimize. So now it's time to test this program in the field, and we did so with 23,000 beneficiaries, mothers in Mumbai. These were divided into 3 groups of 7,667 each. One is the restless bandit group, one is the round robin group, one is the current standard of care. Remember, each mother every week always got a health message. Nobody was deprived of that. What changed is who got a service call. We called 225 mothers every week using this live service calls, basically pulling 225 arms. In the round robin group, it was the first 225, then the next 225, then the next 225. In our restless bandit group, it was the ones who had the top Whittle index. And the current standard of care, no calls went out. That's the current standard of care. And now we want to know how many more health messages are listened to in each of the groups compared to the current standard of care. And here's what we find. Along the x-axis are different weeks. Along the y-axis is cumulatively how many more health messages are listened to. And so you can see with orange, which is round robin, there's hardly any improvement over the current standard of care. But with the restless bandit, with the Whittle index, we get 600 more messages listened to. The point is that if you call these mothers round robin, random, etc., there's hardly any improvement. We want to optimize, and restless bandits gives us a good way to optimize these service calls. We can show that this restless bandit approach cuts by 32% the drop-off rate over the current standard of care. And now we also wanted to show statistical significance. I asked our PhD student, Aditya Mate, to go talk to the Harvard Statistics Department office hours. I thought he'll come back, say, run this z-test, blah, 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 and we'll get the result. And he came back and said, they don't know how to do this test, which I thought that can't be. But finally, after they wrote a paper, then we wrote a paper, and finally, AAAI 25 is when we were able to show statistical significance of these results. This is because this optimization of resources is a very interesting topic for them as well. But we can do better than this two-stage. And here, I want to get us to remember, so the two-stage model, first we maximize learning accuracy, then we optimize. And in many applications, we are told, if you want to improve performance, just keep improving your predictive accuracy. And that's what we were also trying to do. But the main lesson, what we learned from our field trials, is that maximizing learning accuracy did not lead to maximizing decision quality. And in fact, I can show this with the real-world results. So there's two data sets from Arman, orange and blue. Orange has a higher predictive accuracy. So therefore, we would say that if we did service calls based on orange, we would get better listening behavior from the mothers compared to blue. But in reality, the results are exactly the opposite. We got better results from the blue data set, despite lower learning accuracy. Now, why might this happen? So Kai Wang, in his PhD thesis, gives the simple illustrative example. Along the x-axis are some features. Along the y-axis are transition probabilities. The blue are all low-risk mothers. Red are high-risk mothers. Now, if you say, two-stage model, give me something that maximizes learning accuracy, it's going to learn this green regressor line, which great in terms of learning accuracy, but it misses all the high-risk mothers that we really want. So high learning accuracy, low decision quality. Decision-focused learning modifies the loss function to directly maximize decision quality. So now we get this green regressor line, which is terrible in terms of learning accuracy, but gives us high decision quality. And fortunately, we had written a paper with Bisra on decision-focused learning just before, so we could appeal to that technique. And so in decision-focused learning, the idea here with two-stage, we are trying to maximize learning accuracy, maximize how accurately we predict the transition probabilities. In decision-focused learning, we are trying to differentiate through the optimization problem. And this requires us to show that the Whittle index itself is differentiable, and is part of Kai Wang's thesis. More recent work that we've done with Sanket Shah's thesis is to show that we can avoid all this differentiable optimization and directly learn the loss function. But in the actual implementation, we went with Kai's work. And so here we did another trial with 9,000 beneficiaries, 3,000 with decision-focused learning and restless bandits, 3,000 two-stage and restless bandits, 3,000 current standard of care. If you looked at predictive accuracy, two-stage higher predictive accuracy. Now we give service calls based on these models. Along the x-axis are different weeks. Along the y-axis, cumulatively, how many more health messages are listened to compared to the current standard of care. Clearly, decision-focused learning leads to higher amounts of listening behavior. So decision-focused learning with restless bandit is what we've deployed with Arman. The system is called Saheli. Saheli is an acronym. It also means a friend in Hindi. This just to tell you that we've spent enormous amounts of time coming up with this good acronym. So we, since its deployment in April 2022, it's benefited 350,000 or more mothers. We can show that it's prevented 30% drop-offs. And for very low listeners, bottom 25 percentile, the listenership has more than doubled, 130% increase. So does that listenership increase actually translate into improved health behaviors? So there's another study that was done with 21,000 beneficiaries. And here we divided them into intervention versus control group, and with matched intervention and control, we are able to show that actually there is improvement in health behaviors. Mothers are taking more calcium tablets, mothers are taking more iron tablets, they know more about the baby. So this AI is not only improving listenership, but actually translating into improved health behaviors. I want to play a small video of one of the mothers being interviewed. And so here it is.
मी तो फोन नव्हते ऐकत पहिला त्याच्यानंतर मला त्या ताईंचा कॉल आला त्या घरी आल्या मला समजवलं हा कॉल घ्यायला पाहिजे तुझ्या पोरांसाठी चांगला आहे हा मग तेव्हा मी कॉल घ्यायला लागले आणि ते कॉल ऐकून खूप बरं वाटतं की कोणीतरी घरचंच मला कोणीतरी समजवायला येतंय मग जसं ते कॉल ऐकते मी तसंच मी माझ्या पोरगीचं संगोपन करते.
So I grew up in Mumbai, so this is a mother in Mumbai speaking my mother tongue, Marathi. And so as such, it's really very satisfying to see that these mothers have benefited from the research that we've done. But beyond just maternal and healthcare, there are many other public health challenges where restless bandits can be helpful. In collaboration with a faculty member in Harvard Medical School, we're looking at hospitals in Uganda and Ghana, where mothers come out in the maternity ward and there's very few limited wireless vital sign monitoring devices. So which mother should get those devices? There's a resource allocation problem. Or when we think about tuberculosis prevention or diabetes prevention, in tuberculosis prevention, a patient is supposed to take pills for 6 months. I get tired if somebody asks me to take pills for 6 days. 6 months is a long time. People drop out. And now we want to assign health coaches to motivate them to continue to take their medicine. In all of these resource allocation kinds of problems, restless bandits can be useful. And we've shown this with various simulation studies. But the other side of AI for social good is, of course, that we get interesting challenges for improving our AI. And there's lots and lots of challenges with restless bandits. For example, generalizing the restless bandit model, online learning, robustness, fairness, and so on and so on. I'm going to talk about just a couple of papers in the generalization thread, not have time to do rest of it, but consider that the restless bandit model I've introduced so far, there's one arm that controls one patient. So you intervene or don't intervene on this particular patient, this particular mother, for example. However, you can imagine that there could be multiple interventions on a single mother. We may not only want to call her, but maybe text, send a health worker to their home. So multiple interventions on any single person. And then we may also have the case that one action impacts multiple people. So for example, a health worker goes to a village, she gathers together all the mothers, educates all of them. Now, in these kinds of cases, Whittle index doesn't apply. So now we turn to reinforcement learning. And here to learn this intervention policy, and here I wanted to highlight that if we use feature-based Q values, we get improved generalization. So this is computing the value of the restless bandit, and lambda is a Lagrangian multiplier, B is the budget. And now we are trying to compute the Q values of all the arms. These Q values are based on the features of these mothers, age, income, education, et cetera. What this means is the more mothers, the faster the generalization. So this is unlike traditional multi-agent RL, where more agents can lead to slower generalization. Next, now that we've gone into RL, the next question is trying to use data from a smaller village where we may have a lot of data to a village where we may not have enough data. And so we want to be able to use data from the source village to the target village. Unfortunately, some behaviors of some of the subpopulations may be different. Some transition probabilities may differ. There's a dynamics gap. So maybe there's 10 subpopulations. Some of them behave differently in the target village. If somebody could just magically tell me where is the dynamics gap, then for the subpopulations where there is no dynamics gap, I can reuse the source village data. And for where there is a dynamics gap, I can do more exploration. But doing this efficiently requires some effort. And so in recent work, postdoc Ling-Kai Kong has focused on these diffusion model composite flow methods, where you first learn a generative model to learn the transition dynamics of the source domain, and then from the source domain, another generative model to learn the transition dynamics of the target domain. And in the process, you can figure out what's the dynamics gap. And he's able to formally show that this is a principled way to estimate the dynamics gap that approximates washer sign distance. So I'm going to end this section here with 3 key takeaways. If you're working on a public health resource allocation problem, restless bandits is a good tool. If you're working on predict then optimize tasks, then for real, decision-focused learning can actually help. And finally, social impact and AI innovation going hand in hand. This bringing restless bandits and decision-focused learning is one example of that. So next, I want to talk to you about collaborative bandits in Kilkari. This is the world's largest mobile maternal health program. There may be many more than 3.5 million mothers who are registered in this program at one time. And it's a government of India program, very similar to the Mitra program, weekly messages going out, audio messages. This is also managed by Arman. The one big difference here is that we do not get any access to any feature information, age, income, etc. Government will not give access to this information to Arman. There's no way they can give access to Google or Harvard in this case. So what can we do? So here we are focused on identifying the preferred time slot to call a mother. In the smaller Mumbai-based program, Arman figured out, or they had surveys, exactly what time to call each mother. In this case, it's a nationwide program. Rural mothers, mothers in very rural areas, we don't know what time might they pick up. For example, mother number 1 won't pick up a call at 8 a.m., won't pick up a call at 12 noon, will pick up a call at 2 p.m. Mother 2, not at 2 p.m., but will pick up at 9 a.m. or 10 a.m. Current work done by Johns Hopkins essentially relies on calling these mothers 9 times at random, expecting that maybe one time the mother will pick up. And if the mother doesn't pick up, the message is gone. We want to see if machine learning can help. And here, we rely on stochastic bandits. So the basic idea here is that each time slot is a bandit arm. Calling in that time slot is like pulling the arm. And then if the mother picks up, that's a reward for that arm. So this mapping was, so our postdoc Panos Danasis came up with this idea on a midnight call with Arman, that stochastic bandits can be useful. And so once that is determined, we can use standard algorithms like UCB to try to figure out the favorite time slot for a mother. However, so what we are trying to do, we are trying to learn this beneficiary pickup matrix. Along the rows are different mothers, along the columns are different times to call these mothers. And for example, this is the highest probability at 8 a.m. for mother number 2 to pick up the call, and so we will call her at 8 a.m. But trying to figure out this whole beneficiary pickup matrix by treating each mother independently is inefficient. Instead, we can apply collaborative bandits. So basic idea here is to learn from, arms learn from each other. These mothers basically have some similarity that we can figure out. And so we can in fact show that this matrix is a low rank matrix, meaning that there's some similar behaviors that are governed by latent factors among these mothers. And so we can use low rank matrix completion algorithms that work without access to features. So here's how they work. Supposing there's some real pickup matrix, we have Z. We don't know what it is. We will do some trial calls in some slots for some mothers. So now we know for some of the matrix entries, Mij, the pickup values from these mothers. Now we want to optimize by estimating a matrix Z bar, where the entries of Z bar are as close as possible to Mij, but we have a low rank matrix. And so this kind of minimization, so if you read our papers, you'll see we've spent a lot of effort trying to come up with different approaches to come up with these low rank matrices. But just in the interest of time, let me go to the trial we ran. So this was run in the state of Odisha in 2 districts, Kalahandi and Puri. And here we divided the populations into here 2 groups. So there's a control group and there's an intervention group. 6,400 beneficiaries in each group. And there was a 3 weeks of pre-intervention calls at random. And now after that, 2 weeks where the intervention group got our collaborative bandits algorithm treatment, and then the control group got no treatment, continued with random calls. Now the pickup rates in the beginning for the control and treatment groups are different. And so we do a difference in difference regression analysis and show that we have a stochastically significant improvement. But we wanted to understand exactly what is happening in terms of pickup rates. So if you look at these 2 populations, there's a bottom 7% of users who never pick up, top roughly 40% who always pick up. So really the game is in the middling range where there can be an improvement. There's 7 time slots during the day, and we want to know where is the maximum improvement coming from. And what we find out is that slot 6 is where there is significant improvement in terms of higher pickups. So our algorithm is able to figure out that really we should be calling these mothers in slot 6 versus different slots and so forth. So this successful pilot test has led to newer trials in 2 different districts in 2 different states in India, Andhra Pradesh and Assam. And hopefully this will, if this succeeds, then hopefully this will lead to further deployments and so forth. So the main lesson to take away from here is that collaborative bandits can be useful to handle limited data. Before I end this section, I wanted to talk about work we did with HelpMum, which is a nonprofit in Nigeria. We worked with them to develop this model called Advisor. It's an AI-driven vaccination intervention optimizer. Which mother should get a bus ride, which mother should get a coupon, all of that. We wrote this paper, we were done with the collaboration, and we're happy that some paper had been written and all of that good stuff. Very happy, AAI-24, they deployed the model and were able to show that indeed for 13,000 beneficiaries, there was an uptake, improvement in vaccination rates for babies. So that's a really very pleasant surprise. Let me now turn to the third part where I come to HIV prevention. So all of this, again, I wanted to express my gratitude to CAIS and to Professor Eric Rice for introducing us to this whole area of work. And so here's 6,000 youth who sleep on the streets of LA. So this is work done with Eric. And so these are youth who are experiencing homelessness, and we want to spread information about HIV. We can't talk to all of the individuals individually, so therefore we try to find peer leaders. The idea is that the peer leaders, you educate them about HIV prevention, they will talk to their friends will talk to their friends, and in this way information to spread in the social network. So in Brian Wilder's PhD thesis, he came up with a newer algorithm for figuring out right kinds of peer leaders, influencers to find. A quick result here, this was done, 750 youth study right here in LA, 250 in the change arm. This is Brian's algorithm at work. 250 with degree centrality. This is bring in the most popular youth. And 250 with a control group. That is no intervention at all. And at the end of 1 month, we wanted to look at reduction in condomless anal sex, which is one of the HIV risk behaviors. And we can see that with change, there is a significant reduction, but not so much with the other, nothing with the other two approaches here. And in fact, there's in the Journal of AIDS work, in the paper, we have many more of these results. I presented this at an HIV prevention meeting for Africa. And that got me connected with this group in South Africa, which is trying to optimize HIV testing. And motivation here is that estimated 6 million people worldwide do not know their HIV status. And so the key research challenge here is not only that we have a limited number of HIV tests, but we have limited number of health workers to try to persuade individuals to come in and get tested. And so World Health Organization has recommended network-based testing. And our observation from this real-world data is that these transmission networks, for example, HIV transmission networks, are sparse and tree-like. So in our first approach that we've done, we assume that we are given an HIV transmission network. We'll relax this later, but for now we assume we have this network. This is a tree structure, and now each node has a status, positive or 1 or 0, and this follows a joint distribution drawn from a Markov random field. We assume there's a Markov property, so for example, if we know the status of X1 and X3, they are positive or not, then we can know that X6 status is independent of X4. We are going to do frontier node testing. So we will test the neighbors of, if we tested X1 and X3, we test X2, X4, and X6, neighbors of the nodes that we have tested. That's the frontier. And now what we want is a budget constraint policy, node testing sequence to maximize positive detections. We find that this problem of network testing on a tree is very much, can also be mapped into branching bandits. And this is an old paper in 2003 where they showed that Gittins index is optimal. And so now, so just to sort of introduce briefly Gittins index, we had introduced Whittle index earlier to rank all the beneficiaries. Now we're going to use Gittins index to rank who to test. And it's essentially giving us what's the expected value of testing in the tree, in the root of a tree. And so our contribution here has been fast computation of this Gittins index. So the basic algorithm is you input some graph. That's the original graph that's given to us. Maybe it's not a tree. We walk that graph to convert it into a tree. We compute the Gittins index of all of the nodes. And next, we find the frontier nodes to test So we select a the node with the highest Gittins index, test it, and then we find the frontier, find the node with the highest Gittins index, and repeat in this way. In simulation studies, this is a real-world HIV-sex interaction graph. The frontier nodes are circled. Along the x-axis are numbers of HIV tests. Along the y-axis is cumulatively accumulated rewards, that is number of positive individuals that we found. The orange is the Gittins index policy, that's ours. The other two are baseline, for example, greedy or deep Q network. And then the red is random, and we can see that at, for example, 150 tests, that we can find far more positive individuals compared to these other baselines. So we are excited. So there's in our paper, which is on arXiv, there's a lot more of these results. We're excited for the tests that are going to follow in collaboration with WHO and Gates Foundation in South Africa. So the main point to take away is that network approaches are useful for HIV testing and prevention. I'll end this whole health section by talking about some recent work we've been doing with the government of Ethiopia. Here, the challenge is where to build complex health posts or hospitals, such that we ensure that every person in Ethiopia is within 2-kilometer walking distance of this health post. And so this is like a facility location problem, except we have to have fairness and equity across regions. The population is growing, and there's online budgets. So taking all of these things into account makes it a challenging problem. And then humans might want to give advice, which advice to give, to take and not take. So those are problems. So this is a paper under submission. Okay, that brings me to the final section for the last 5 to 10 minutes of my talk, which is this multi-agents for speeding up social impact. So for the past 20 years, the way things have worked is that some nonprofit, some government agency will come to me and explain they have some kind of a resource optimization problem. Literally with Arman, it was like we were sitting in a Starbucks in Mumbai, and the founder said, well, we have a problem that people are dropping out of our program. Can AI be used to prevent that? Okay, so that's from there, really trying to dig deep into exactly what is their domain, what are the challenges, to arriving at, we are going to use a restless bandit, was many, many months of discussions going back and forth. It's a very labor-intensive process to truly understand exactly what was their constraint, why we couldn't just do something simple, et cetera, et cetera. And then, of course, evaluation takes a lot of time. So our question is, can we speed up all of these processes using LLM agents? And so I'm going to focus here on the middle part of this, which is coming up with, for example, a restless bandit model using an LLM agent. And in particular, the aspect of the problem I'll focus on is this. Supposing we have already developed a restless bandit model, and we can learn a policy using reinforcement learning for their original goal of maximizing performance across all beneficiaries. Now suppose they say, we want to slightly change our priorities. For this month, we want to run a campaign where we want to slightly prioritize low-income beneficiaries. Today, the way this would happen is they would come to me, we would change the code and generate a new policy. And our first step here was to build this decision language agent to automatically generate this policy from this natural language command. And so this is done by autonomously searching through the reward functions. And so essentially, you remember that we had this restless bandit MDP, where good state gave us a reward of 1. Now if we say we want to slightly prioritize low-income beneficiaries, the LLM is going to go through and generate lots of different reward functions. For example, for R1, which is one of the candidates, we'll give 20% more reward if we pick an arm, which is we have somebody in good state, but they're also a low-income person. With R2, we're going to subtract 20% of rewards. And so there's all of these different reward functions. We feed them through our restless bandit RL and see, does it produce a satisfactory policy? To make this more concrete, the way this worked is that the restless bandit code with the restless bandit code base and language command, like slightly prioritize low-income beneficiaries, all of this is fed into Gemini. This generates multiple different reward functions, so code for different reward functions. These are fed into restless bandit models. With RL, we train different policies, and then we run this, in this case, in simulation to see what is the impact. So for example, with policy 1, we are giving more resources to middle income beneficiaries, which is not what we want. And we can also generate similar who gets the resources kind of a graph for age and education, other features that we have. And similarly, we can do so for different policies that we generate. In this case, then we feed all of this information back into Gemini, which realizes that policy 2 meets the criteria that we were looking for, giving more resources to low-income beneficiaries. And so then it can iterate and improve. So in our NeurIPS paper, we show that compared to a human, so the human here is yellow, gold standard, and so a human is always 100%. Right or wrong, we ask the human, take this command and write a reward function for a restless bandit model. And whatever the human did, that's the gold standard. And then we ask Gemini to do the same, and Gemini's results are shown in green. And we can see that for simple commands, green approaches yellow. As the commands become more complex, sometimes green is further away from yellow. And in fact, where the difference is more prominent is when we have a multi-objective command like prioritize low-income beneficiaries and low-age beneficiaries. Here, Gemini can generate independent rewards for each of the different commands, like low-income and low-age. But how do you combine them, because it's a multi-objective command, to generate a single policy? So we turn to these p-means social welfare functions. This is a way of aggregating different utilities in order to generate a single value. And what's nice about p-means is that with different values of p, we get different kinds of social welfare functions. For example, p equal to 1, utilitarian, p equal to minus infinity, max, min, or egalitarian, and so forth. And now we want to, so if you give me one p-value, now my problem is to find a policy that maximizes the scalar value that is returned by this p-means function. The challenge, of course, is who's going to give me a single p-value since there are so many of them. And so our approach here is to return a portfolio of policies so that with certain guarantees provided. So for example, for any p from my portfolio, from my finite set of policies, I'll have one policy that's alpha approximate. So I'll come back to you, in this case, for example, with 3 policies for this command, or red, blue, and green. And each of them, as you can see, makes different trade-offs in terms of resources given to people of different education, of different age. But now you tell me what p-value you want. Whatever p-value you want from the whole p-means, one of these policies is guaranteed to be 0.98 optimal. So this is something that we can generate via portfolios. So the last little bit I wanted to discuss is we have also been working with task-specific LLM tuning so that rather than doing all this inference time work, we can directly generate a reward function. So this is a robust DPO, and this is just showing that with inference time, with the decision language model, which is shown in red, we can see that there's more and more inference time if you have more and more people to work with. With our recent work with this DPO, basically there's hardly any improvement, there's no change, so we can generate these reward functions very fast. So this is the end of my presentation. To give a summary, I first talked about Bandit algorithms to optimize resource allocation in public health. I've talked about working with the world's 2 largest mobile maternal health programs, and then that this restless bandit model can be useful for other public health challenges, tuberculosis, diabetes, and others. Next, talked about networks for HIV testing and prevention, and finally, multi-agents to speed up using these LLM agents, the whole AI for social good enterprise. I wanted to quickly talk to you about lessons we have learned. So there's 3 types of partnerships that we have in AI for social good. First is the AI-human partnership. So lessons here are that it's important to make sure that we give appropriate roles for humans versus AI. To make sure that we use the right expertise of the humans. To give you an example, in the case of Arman, we were giving the mothers were getting calls from the call center. The call center workers were giving calls to these mothers. It was not the AI giving calls. The AI was only determining this is the mother to call, but what to discuss with her was not done by AI. And we have resisted pressure to get AI to talk to these mothers because this might be the only human contact they may have, and they may reveal things like domestic abuse or many other complicated situations where a human can really deal with those better. With respect to sort of these types of works, we often want to make sure we have deep interdisciplinary partnerships. We don't want to be engaged in helicopter science where we drop into this community, kind of take their data, maybe write a paper critical of them and leave. In prior work we've done with wildlife conservation, the first trip I went to Uganda, the government person there told me, we're not going to give you our data because the last research team that came here took our data, published a paper critical of Uganda's wildlife conservation policies and ran away. And so we had to kind of spend a lot of time trying to explain to them, no, we are going to be here in the long run. We are going to help you to really try to tackle this problem. So we don't want this kind of helicopter science. And then finally, we of course want partnership with the real world. We want to look at the entire data to deployment end-to-end pipeline and patience in trying to come up with the right problem, because this task of, the first thing you hear is some we want the health workers to become more efficient. And you're sitting there, okay, so what does that mean? To finally realizing this is some kind of a bandit model takes a lot of time. And so I hope you will have the patience to kind of deal with these. So that's it. Thank you so much for listening to me. Really appreciate your all being here. Thank you.
Thank you so much, Milind. Always perfect timing. So we have a good time for questions. We have 10 minutes for questions. So go ahead. Cassie will be taking questions from the people online. So if you're online, please start writing. And we have mics on both sides of the room. So if you have a question, just start heading to the mic and asking there. Anything online, Cassie?
Yes.
Yeah. All right.
First question, how LLMs can be used as a whole for many of these problems on different levels, but in particular for figuring out by IE reasoning when to call the mothers of different subpopulations.
So I'm not sure I entirely followed the question, but I think, the way we are using LLMs is really to define the reward functions that will define the policy. So in some sense, the optimization engine is outside the LLM. It's optimizing. And the LLM is only generating code to generate the optimization function, something like that. I don't know if that answers the question. Go ahead, please.
Thanks for the nice talk. Actually, I just wonder, in the last paper, if we learn the optimal policy through feeding a data in LLM agent, it seems to be there need a lot of annotator to feed data, but you're working on the large scale optimization, so I just wonder.
Yeah, this one. So I think you're right. So the idea here is that we are generating the reward function rather than doing all that inference time reasoning. Rather than we are directly generating the reward function. You're exactly right that we need lots of annotators for good and bad reward functions. Right. So our idea here has been to use another LLM as an annotator, and therefore the annotation is noisy. And therefore, we need a robust DPO. And so that's basically the line of work here.
Oh, I see. Thank you. Actually, can I ask one more question?
Please.
Thank you. In the same paper, it seems to be very familiar with the multi-objective optimizations. And in this problem, I see a lot of problem that discusses about the trade-off between each objective, since in practical problems, it is often that each objectives are quite incompatible. So
compatible or incompatible?
Incompatible. So there exists a trade-off between each objective. So I just wonder what's the main approach to deal with this trade-off in this paper.
So that, as I showed here, the basic idea that we use is this idea of generating a portfolio of policies with different p-values. So essentially, you give me your multiple objectives. I'm going to return to your portfolio of policies 3 policies. And now, no matter what p-value you choose in this range, one of these policies is going to be, say, 0.98 optimal. So that's the way we are dealing with it in terms of returning, in terms of dealing with multiple objectives, which is to say, we are not going to pick the right trade-off point. We're going to return this portfolio. At least it kind of reduces the amount of search that the human has to do. And it's a finite-sized portfolio. And now you tell us from this portfolio, you know, any p-value, and one of these policies is going to be, you know, optimal or 0.98 optimal, etc.
Oh, I see. Thank you.
Hi, Professor Tambe. Thank you very much. I'm interested about the Bandit algorithm for kind of maternal health. You know, in the predict and then optimize paradigm, you talk about like you can use machine learning to kind of learn the transition probability, but like kind of what is the data set for learning that? Because like, do you get like the transition probability directly, or do you somehow infer the transition probability from some prior kind of other kind of data?
So the data has 43 features for each mother: age, income, education, time, preferred time to call, language spoken, prior pregnancies, blah, 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 all these kinds of things. And then their track record, like was in a bad state, didn't get a service call, transition to a good state, service call, bad state, et cetera, et cetera. So we have all of these kinds of you know, states that the mothers were in and whether they got a service call or not. And so based on that, we are trying to learn to predict their transition probability. So when a new mother of similar age, income, et cetera, comes in, we can predict the mother's behaviors. Okay. And so does that answer your question?
Is there like a established algorithm to learn that, or because
I mean, that's you know, you can imagine it's a logistic regression. I mean, you can use a simple neural network to learn that. So that's part is fine. Okay. There's no problem in that. I think the issue becomes that if you use first predict and separately optimize, that doesn't work as well as kind of doing this end-to-end learning.
Okay, I see. Yeah, thank you very much.
Hey.
Hi, Milind. Fantastic talk. Thank you so much for that. I was very curious about your statement about AI progress going hand in hand with social impact. So one thing I was thinking about is like in the first project, the Arman project, where you had interventions in terms of like messages that you were sending these mothers. One thing that comes to mind is that because these are human subjects, the content of the message could also have a big impact.
Correct.
And not to say that this is a simpler problem than the problem that you went with, but I am curious how these kind of like more human factors also play a role.
No, that's so there is the automated voice messages that go out, and you're right that the content of those messages could be tailored to different mothers. And so this may be something in the future. Right now, these messages certainly, there are doctors who sort of determine these messages and they've kept it constant. But you're right, this could be something where the agent could kind of tailor the message based on the mother's pregnancy or whatever other data that they might be able to get. So we haven't done that. It's a very interesting problem, and it's just something that can be, yes.
Let's prioritize the people in person for questions.
Cool.
Okay.
Thank you again for your talk. Just going back to the fine-tuning component that you were talking about with the LLMs that you're integrating into the system. So you had mentioned that you're doing like a form of post-training basically via what we can effectively define as simulation-based inference. You have a series of codes that you're producing, whatever the distribution of payouts are for the population, you're based on that, giving some type of signal back to the model that, hey, yeah, do much better in terms of how you're allocating resources. My main question is, well, it's a two-part question. Have you noticed any significant improvements from doing the post-training on the LLM model? And two, have you noticed any emergent behaviors that come from the model when you're incentivizing a greater like distribution of resources for specific like groups?
So you can see some of this improvement here already. So for example, this doesn't get to all of what you're asking, but the dark green bar is this decision language approach without any reflection. So essentially, you just ask it one shot to generate the reward functions and then pick the best out of those. So there is no reflection. You can see that the lighter green bars in all of these cases, except maybe one or two, are higher. So there is improvement by doing this kind of feedback loop to the LLM to say, here's what you produced from the last set of reward functions, and now reflect on those to generate a better one. And why sometimes there is like a lower, lighter green bar, we haven't completely kind of figured out. As to whether there were surprises, honestly, this work was done in around fall of 2023 was when we started. And my bet with the lead PhD student was that LLM is not going to be able to do this. And I was surprised, happily, that it got to this point. Now, obviously, things have progressed a lot more since fall of 2023. But I guess there hasn't been like some weird output that would be like super surprising, that would be harmful. We've done things like, is it fair, and all those sorts of things, and those sorts of results are all in the paper.
I guess just as a quick follow-up, are you guys planning to open source the models that you guys are creating, or the system that you guys have?
I mean, we're working with Gemini, so that Gemini, but the rest of the code is on our website with the NeurIPS paper, yeah.
Thank you.
Thank you, Milind, for the great talk. I noticed in a lot of your projects, you used a lot of creative features or proxies to serve as predictors of long-term health outcomes, especially in your first project. So I was wondering if you could talk a little bit more about what that process of feature engineering or feature selection was like, especially because a lot of the times we are working in these low data regimes where the features that we want are not necessarily accessible to us for very long periods of time. So what can we do as researchers to kind of mitigate for that problem, to account for this uncertainty in missing data?
I mean, as we know in AI for social good, basically we are always struggling with low data, low compute, and low resources. And for example, I mean, just in terms of low compute, we also have the problem that with Arman, they have 1 hour of cloud compute per week. And so whatever you got to do in this hour. And so these are very challenging kinds of problems. And in the second project I mentioned, there is no feature information available whatsoever. And so, we're sitting there trying to figure out, okay, what can we really do in this case? And so I don't know that I have a formalized process of how we arrived at, okay, this collaborative Bandit is the right approach. But there had to be something that allowed us to improve the pickup rates of these mothers, to improve listenership. And so it was like it's just lots of talking to the partner, the NGO, can we try this, can we try this, can we try this? And then finally something seems to stick and they feel like this could work. Yeah. And so that's essentially been the process. And sometimes chasing the wrong solution for a time. So for example, with the 2-stage model, we wanted to improve performance. We actually kept trying to improve predictive accuracy. We got higher predictive accuracy. I wrote messages to the nonprofit partner saying, we are getting higher predictive accuracy, and somehow the performance is getting worse and worse, and we don't understand what is happening here. We had written already these papers on decision-focused learning, but somehow we hadn't put 2 and 2 together, and then finally just sort of like, okay, we had written this paper with toy domains. We really didn't think this was real life, but it's actually real. This is truly happening to us. You keep trying to tweak the model to improve predictive accuracy, and it's actually not helping us at all. And so I guess I don't have a formal method, but it seems like a lot of discussions with our partners, a lot of just trial and error until we kind of settle on the right approach that seems to work. I don't know.
Yeah, thank you. Yeah.
How did you generate the graph?
The LA homeless population.
That's a great question. So there's no graph. There's no graph at all. And so Brian's contribution in his thesis was to cleverly sample from the population. So the idea is to sample 10% of the population, and from that sample, figure out who are the right peer leaders. And formal statement is what to sample such that the influencers you find after the sample will lead to the same amount of influence as if you had the whole graph available. And so here's a formal paper in AAAI 18 to show formal properties, and then an approximation in an AMAS 18 paper where he shows that you can kind of approximate that process. So yeah, there's no graph, it's sampled.
Good evening, Professor. Thank you so much for the lecture. So my question was, can this algorithm be extended to oncological treatment? So basically working with TCR beta sequence responses from RNA for like treatments for leukemia, where the data is large and the matrices are dense. So the chances of overfitting the data, overlearning the data are more. So can we apply like the restless bandit algorithm to cover these areas?
I'll have to learn more about your application to be able to say yes or no about that. I guess if it's a problem where you have a large number of patients, small number of resources to attend to them, and the state of the patients keeps evolving no matter whether you intervene on them or not, then restless bandit seems to really be very helpful.
I see. Thank you so much.
Shall we take one last question from online?
Yes.
All right.
There are several questions about, are there any labs at USC that are doing similar research to this?
Yeah. It's right here, all these labs here, right here.
All right, amazing. Milind, thank you so much for a fantastic talk. Let's thank our speaker, everyone. If you have questions, are you going to stick around for a few minutes,
yes,
Milind?
Yes.
If there's more questions, feel free to come down and ask them. I want to make sure people are free to go to their next lectures and everything. Thank you so much, Milind.